So the goal today is trying to convince you there's an interesting time scale called branching time in the process of scrambling. This time scale, this time is actually defined in the previous paper here, but the meaning of it is kind of obscure in that formalism. Today I'm trying to unfold this time scale. In particular, I'm trying to give you some intuition about what this time scale about from a simple model, a viral spreading model. So that's the first part. Then I will give the actual definition of the branching time in the quantum many-body system. This kind of quantum many-body system needs to have a larger parameter to work with. Then I will discuss the weak coupling limit and the strong coupling limit, what this new timescale plays, what the role of this timescale plays in these two limits. And we will see that it seems to suggest there are two different mechanisms of scrambling. And then I will talk about a upper bound of the branching time. And in the end, I will come back to the weak coupling limit and say a few more things. So here's the plan. Now let me start the introduction. Okay, over the past few years, we have gained a lot of understanding about the information scrambling in the chaos. In particular, we have understand like the basic picture of information scrambling in a unitary quantum system is that the time evolution actually, what does it do is actually take a simple operator to complicated ones. So there are lots of pictures, but this is a particular simple one that can help us to understand the information scrambling. Let's take a simple example. The most simple one I can think of is actually the SYK model. It's kind of structureless. The Hamiltonian consists of a random 4-fermion coupling. In general, we can consider a group of Q fermions. But here, let me fix Q equals 4 for discussion now. So when we have such kind of Hamiltonian, we can derive how the operator evolve on the time evolution. So we can talk about the Heisenberg equation. So the simple picture is the time evolution of a simple operator. So its time derivative is equal to the Hamiltonian commute with this operator, and that's basically just dropping one fermion out. So one fermion, when on the time evolution, will become 3 fermions, and it can keep going. So here's a cartoon for that. You have a single fermion, and at some time it decide to split or branch in some sense. And it becomes 3 fermion, and at a different time it decide to branch further and further. So that's the picture of this time evolution. So after some time, this simple operator will evolve to a superposition of this kind of trees. So they have big trees, small trees, and you need to sum all of them together. And that will be the picture for this operator at a later time t. In this picture, we have a make sense that this operator becomes more and more complicated. For example, we can talk about the size of this tree. So in this case, the size will be defined as the number of leaves in the end. So because the time evolution takes 1 to 3, it becomes a product of 3 fermion operators, and then becomes 9 operators in this case. And the size of this tree, we can say is 9. And due to the nature of this Heisenberg evolution, we can imagine the size of tree actually grows exponentially. To actually quantify this size growth, we can consider the following quantity. So we have this time evolved operator, and we want to count how many Fermi operators involved in a particular configuration. We can simply anti-commute with the fermion operators, and we sum of all of them. So whenever you hit one, you will get one non-trivial contribution. If that's not in this tree, you get a 0. And so this anti-commutator will be proportional to the number of leaves in this tree. And what's left over is a bunch of gamma matrices representing the Fermi operator. And to get an actual number, you take a square of this gamma matrices and take a trace. So that will be the size, the average size of this operator at later time t. So this kind of picture has been used in previous works to explain the operator growth. And you can see that what appears here is what we know as an out-of-time order correlator. In particular, it's the out-of-time order correlator at infinite temperature. So from out-of-time order correlator, you can define a Lyapunov exponent. And due to this relation, you can say that the Lyapunov exponent actually characterizes the growth of the operator. So to be more precise, to be more explicit, let's see so what time evolution gives us from the viewpoint of this this formula. The time evolution, so in general, you can expand this operator in terms of a different number of Fermi operators. This short one, longer one, and they have size s. And the time evolution determines the, so actually you can determine the coefficients here by computing, for example, trace of this operator with the basis here. And they will depend on time, and the time evolution actually shifts the weight from a simple operator to the heavy operators. So that's the basic picture of information scrambling. It's a process of bringing the weight from a simple operator to the more and more complicated operators. Each C coefficient here is amplitude, is norm squared, becomes a probability, and from this you can also see why this size is the meaning of this average size. But also, but there's a drawback here actually. This picture works very well in infinite temperature because all what we have is just this simple formula trace this anti-commutator square, and you basically put the identity here if you want to interpret it as the density matrix. So that's basically an infinite temperature quantity. So this operator growth picture works very well in infinite temperature, and each coefficient can be interpreted as the weight. But when you go to some finite temperature, it's not obvious how this picture works, because this complicated string of Fermi operators may, when you project to low energies, it might give you some very complicated coefficients, and maybe there's a huge suppression of the big operator. So that's just a side comment about this picture. This picture works well in the infinite temperature. Okay. As you can see, this operator growth picture, like one operator splits into 3 and keep splits, is very much similar to the viral spreading. So you can imagine that the viral spreading also grows exponentially, and you can also define similar Lyapunov exponent. So let me try to use this viral spreading model to give some intuition about the different timescales in this system, in the operator growth picture or in the information scrambling. In particular, I want to introduce this branching time. And I will actually use the viral spreading model, which I will define very soon, to derive a simple relation between the different timescales appeared in this system. So one of them is the Lyapunov time, or Lyapunov exponent, the inverse of Lyapunov time. The other I will call it a branching time, and the third one is something analogous to the quasi particle lifetime. And I will show that in this various spreading model, this simple formula holds. And it turns out this simple formula turns out to be exact for a special type of SYK model called Brownian SYK, which I will mention later. Oh, okay, let's start. This various spreading model is basically the simplest one you can imagine. You imagine you have n people and be large, and you start at time equals 0, you have one infected patient. Let me call it patient 0, and we assume the virus spreading is the infection process is kind of a Poisson process. That means we declare that you have a probability gamma per unit time to infect q minus 2 more people. So this special definition is trying to mimic the SYK model, but in this particular picture, I will just set q equals 4. So each time you spread it, each time the virus spreads, it will infect 2 more people. So one sick person will become 3 sick people, and keep going. So we can also label the generations. We can say that this is the generation 0. This is generation 1, you have 3 people get infected. Generation 2, you have 9. Here I make some made some simplifications. So as I said, I assume n is very big. So we consider dilute limit, and we only consider the early time. Early time means much earlier before the scrambling time. Scrambling time means the time scale when almost everybody is infected. So the dilute, so we assume the diluting means to avoid any scenario when you encounter the so a sick person encounter another sick person. So that's the situation we want to avoid. The second simplification we will make is we assume nobody will die. That's good because we don't want a person like missing at some point, and that will simplify the problem. And it's also a good thing to assume. The third assumption I will make, maybe not necessary, but it do simplify the problem. So we assume the infection is kind of synchronized. That means although it's kind of a Poisson process, you can get infected at any time, but when you get infected and the next time what that happens, it could happen anywhere, but let's assume each generation will always get infected at the same time. So let's say there's a time 1 where one person gets infected. There's one person get infected and it becomes 3 persons at one time. And then at another time, immediately all of the 3 sick persons infect 2 more persons for each one. So there will be 9 people get infected at generation 2. That's just a simplifying assumption. It's maybe not necessary. Okay, let me wait a few seconds to see if this setting is clear to everybody. Okay, there's some construction going on in the background, and I apologize for that. Okay, let's see. What's the interesting time scale in this simple model? So the first time scale you can think about is the Lyapunov time or the Lyapunov exponent. So Lyapunov exponent here defined as the growing exponent of the number of infected person. So this is easy to compute. The growth of the number is proportional to the current infected person, and is proportional to the infected rate gamma and also the Q minus 2. So each time you get Q minus 2 more person to get it, to be infected, and then that's the coefficient. So you get the exponential growth, and then the exponent is Q minus 2 times gamma, which is easy to understand. Okay. So the second time scale is something analogous to the quasi-particle decay time. So that's the way we define it is you can try to compute the probability of, so assuming somebody is sick, and you can compute the probability of this person not infecting others. So the probability is actually exponential decay, and here you can define a time scale, the inverse of this rate gamma. It's kind of, well, in some sense, it's kind of the lifetime of being a good person, not infecting others. Okay, so that's another time scale which is related to the gamma. The third time scale I will talk about is called branching time. Here is the definition. So it's basically trying to count how frequently a branch happens. So you have it splits, so there's a branch happening, and you can ask how frequently it happens. So there's a naive answer. So if you focus on the patient 0, and you ask him what's the expectation value of the generation, well, he will give you a simple answer because in the setting we have said that at unit time you have probability gamma be to infect others. So at time t, the total number of branches you can imagine is simply gamma times t. So the branching time will be the naive answer. Branching time will be 1 over gamma. That's the same as the quasi-particle decay time. However, this is not the correct answer. If you ask all the patients, so let's do this. You look for all the sick person and count what's the generation number. So for example, a person here, the sick person here will be in the generation 0, 1, 2, generation 2, and you ask him what's the generation number, and then you collect the data for all these persons, and then you might have a different configuration. That's a different situation when you have maybe more branches, and you do all these things and compute the expectation value. So if you do that computation, so what you do is use the Poisson process, the probability for the Poisson process. So the probability assigned to a tree with n generation is given by this simple formula. And for each kind of tree, you have q minus 1 to the power n infected person, and each of them will report you n. There's their generation number, and then you divide by the total number of patients here. So if you do this calculation, you will get a different answer. That's q minus 1 times gamma times t. So the branching time here will be, or the branching rate will be q minus 1 times gamma. And then that's actually the correct answer, because you do need to ask all the patients to get the actual data. So where the correct way to measure this is to average over all the patients, not average over all the tree configuration. This is because so the discrepancy between these two answers actually reflects the fact that when the generation number becomes bigger, there are more people, exponentially more people get it, will stay in that configuration, and they will shift the weight of your statistics, and it will significantly increase the branching rate, so it becomes amplified by q minus 1. Okay, so that's the plan. Yeah, please.
Sorry, I was trying to ask maybe 2 slides earlier. Sorry for interrupt again. So I was wondering, say, the question is very naive, is that what's the main motivation to consider this model? Is it because this model has some universal behavior that you want to capture?
Oh, I want to give a classical interpretation of the branching time. I want to introduce the actual definition. So that the actual concept I want to introduce is defined in the quantum system. But I want to give a simple picture on what this timescale is about in this simple model. And in fact, the simple model do have a quantum analogy, which I will discuss, is the Brownian SYK. So, and I will also show that in the simple model, this timescale do have interesting relation to the other 2 timescales.
Okay,
so
thank you
for introducing this model.
Thanks.
Thank you. Any other questions about this model? Okay, so now we have 3 timescale or 3 rate in some sense. First is the scrambling rate, which is defined by the Lyapunov exponent. It's q minus 2 times gamma. Second is the cost-particle decay rate, or you can also see that's the naive branching rate. That's gamma. And the third quantity is the branching rate. That's q minus 1 times gamma. That's what we just computed. That's given by, can be determined by the average number of generation measured for each patient. The average number of generation is here defined as the total number of time over the branching time. Okay. So from these 3, we can try to eliminate the Q dependence. Q is kind of not an interesting number in this system, and we want to eliminate it. We will get an interesting formula. The scrambling rate is equal to the branching rate minus the, in some sense, cost-particle decay rate. Or you can say, or you can interpret it the other way. So like the Lyapunov exponent scrambling rate is actually the gap between the actual branching rate and the naive branching rate. So we get this formula from this simple model. And I'd like to make 2 comments. First comment is, although this is a classical model describing the viral spreading, and as I trying to motivate in the beginning, it's related to operator growth picture. And it actually, the calculation and the results here actually has an exact counterpart in so-called a Brownian SYK model. So the Brownian SYK model is a variance of the SYK, but without actual time translation symmetry. So the coupling constant here will be time dependent, and it's still a random coupling, but we make it uncorrelated in time. So what we actually do is to impose this coupling constant is a delta function in time. So that's what we usually do for the Brownian motion. And this model actually has very much the same property as the this viral spreading model I just discussed. And in the important feature in this viral spreading model is each event is uncorrelated. So it's independent because we are assuming it's a boson process and each event is uncorrelated. And this is the same as in the Brownian SYK model. Each interaction vortex is uncorrelated. And that's different from the regular SYK, where you need to pair each vertex with its partner. And there's a non-local in time correlation. So you can expect, and indeed that's true, this kind of relation does not hold for the regular SYK. Later we will discuss how accurate this kind of relation is in certain limits. Okay, so that's a comment about this viral spreading model. The second comment is that here we gave some intuition about this branching. So we said the scrambling rate is the branching rate minus the quasi-particle decay rate. So in some sense, the branching is the driving force of the scrambling, and that's also clear from the operator growth picture. Each splitting makes the operator size bigger, and then that's the signature of the scrambling or the operator growth. However, as I mentioned before, this kind of intuition is only good in a high temperature. So you cannot, there's a warning sign, so you cannot push this intuition too much to low temperatures, because as I mentioned a few slides earlier, in the low temperature, you need to insert a density matrix to define the OTOC, or to define the scrambling, which we, in this case, we defined by this OTOC. You need to insert a density matrix, and this insertion of density matrix will do something to the operator strings here, and that part of the calculation is not captured, and it's not captured in the operator tree, operator growth picture, and that might cause some problem. And indeed, we will see that in the low temperature, the physics is quite different. So that are the two comments about this operator growth and the viral spreading model. Is there any question about this classical model and the intuition of this branching time? Now let's move to the actual quantum mechanical system with large number degree of freedom, and to give a quantum definition of the branching time. So the branching time, the intuition we get is the branching time basically describes how frequently each operator splits, and let's try to define that in the quantum system, and also we allow a finite temperature. The analog of the operator growth picture, or the tree picture, is actually the ladder diagram. And indeed, in a large class of quantum many-body system with larger degree of freedom, for example, the most familiar class is the SYK-like model. The OTOC is actually computed by summing the ladder diagrams. This is true in SYK, but it's also true in some other type of model, like weakly coupled matrix models. Although it's not obvious, but if you're trying to compute the out-of-time order correlation function, it turns out the leading diagrams are still the ladder diagrams. So when you have such a kind of ladder diagram, there's a natural time scale you can define just by looking at this picture. It's the average time separation between the branches, or between the rungs. Let's call this rungs. And these rungs just some fields interact with the probing field that's represented by this line. So this could be a composite operator. For example, in SYK, each interaction vertex consists of 4 fermions, and this rung is just a product of 2 fermion propagator. And in this picture, we can define average time separation here. So that will be our definition of branching time. To connect to the previous picture, in the previous picture, we have a pair of we have a big tree, and we define the branching time to be the average time separation between two nodes, basically, and how frequently it branches. And we give each tree a proper weight. For example, in that weight, the assignment of the weight depends on the model. For example, in the various spreading model, we assign some probability to this tree according to the Poisson distribution. So that's basically what we do. So we consider the average time separation, and we weight each configuration by some sense the inner product of this tree. And if you really compute this inner product of the tree in a quantum mechanical system using Feynman diagrams, and that actually gives you the ladder diagrams. So for example, we are focusing on operator J, splits, and the target is operator K. And you can move all the branches to the vertical line here. And the inner product will just glue in these two pairs. So this slide is trying to show that the intuition we gain from the classical model or from the operator growth is actually consistent with the definition here in the ladder diagram. So the average splitting between two branches here is basically the average splitting between two rungs. And what we do in this, so what we really impose, the new ingredient in the quantum setting, probably with finite temperature, is that this ladder diagrams provides a suitable inner product or suitable assignment of the probability for each tree. Okay. So here we have a diagrammatic definition of the branching time. That's the average separation of two rungs. And each diagram has its own weight given by the amplitude computed by Feynman diagram rules. That's if we want to actually compute that, we can follow the same strategy. We're not computing the time directly. We first count how many rungs on average you have for a given time t. And that can be done very efficiently. I will show a computation trick to do that. So the out-of-time order correlation function itself can be organized as a summation of the different ladder diagrams with different number of legs, the rungs. So F0 is this, F1 is that. And then the average number of rungs is defined to be weighted sum of that. So it's n times Fn and over the normalization factor itself. So Fn over OTOC serve as the probability distribution for the number of rungs. However, it still seems to be a difficult task. So imagine you have some complicated propagators, and you need to compute. This formula seems to suggest you need to compute each Feynman diagram, which might be still complicated. We need a trick to do that. The trick is to use the generation function method. And we assign a fugacity to each rung. And we define a generalized out-of-time order correlation function with a parameter mu, kind of mechanical potential. And when we have that, we can then obtain the average number of rungs by the usual trick. We take a log derivative of this kind of grand partition function. And we will get a simple formula because we have an expectation that this out-of-time order correlation function has to grow exponentially in time. So it will, the time-dependent behavior, the time-dependent part will behave like exponential lambda L times t. And when we take derivative to mu, it directly take the derivative on this exponent. So it becomes lambda derivative with respect to mu, and I take a value at mu equals 0 and multiply t. So that's the actual growing part in this formula. So in general, there will be other parts, but none of them will grow. And from this formula, we see that average number of rungs equals this number times t. So you can interpret the inverse of this number to be the branching time. So the branching time in this calculation using this trick will be simply be captured by the derivative of Lyapunov exponent. So the task left over is just to compute the Lyapunov exponent as a function of this mu. And there's a useful method that has been used in the literature, the out-of-time order correlation function, or the Lyapunov exponent, can be obtained using a simple method called the retarded kernel method. So the basic idea of retarded kernel method is that the out-of-time order correlation function is actually approximately an eigenvector of an integral kernel. As we said, the sum of ladder diagrams is represented here, and you can write a basically two-particle swing Dyson equation. So this, or some literature called beta cell beta equation, but that's this is a double Cavendish version of the beta cell beta equation. So it consists of, so it can be written as a kernel multiplied self plus the free term, the simplest term. And this kernel is just the elementary part of this diagram. So it's represented here. It consists of retarded Green's function, advanced Green's function, and the rank function. Since this trivial part is not growing in times, in the late time, the important piece is the out of time part. So you will get an approximate equation that out of time order correlation function is a eigenfunction of the retarded kernel with eigenvalue 1. And the retarded kernel you can obtain just by multiplying the correlation functions in your theory. And then the rank function, the actual form of the rank function depends on the model. And for example, in the SYK model, that will be the product of Whiteman function of SYK. But well, those are just details now. So important, the point is you can determine this kernel just by solving two-point functions. Okay, when you have this kernel, so our goal is to compute the branching time, and that has been transferred to the computing the Lyapunov exponent as a function of this fugacity mu, chemical potential mu. So when we have this formula, we can have a recipe of computing this branching time. So this part is kind of boring, but let me just provide the recipe of computing the branching time. So the goal is, so the equation indicates that out of time order correlation function is an eigenvector of kernel with eigenvalue 1. So we can search for that solution. So first, by simplifying this kernel. So what we know is this kernel, you can interpret it as an operator acting on function of 2 time, T3, T4, and it has a time translation symmetry. So in particular, it has this time translation symmetry that you can move the central mass time for T1, T2, and the T3, T4 together. So that means this operator actually commutes with the central mass time translation. With this symmetry, you can then diagonalize your space that basically diagonalizes big operator using a good quantum number. That's the growing exponent. Growing exponent in the sense that it acts on function of time T3, T4, so it's a function of 2 time, and the growing exponent is defined with respect to the central mass time of these 2 times. So doing that, introducing that, you can simplify your kernel and further use the global time translation. The final form of the kernel will be a function of 2 times. So it's just a relative time. it maps the function relative time to a function relative time, and it labels by the quantum number lambda, which has the meaning of the Lyapunov exponent. And that's basically the kernel we have. And and you can also, well, since you have this, you can basically do the numerics in the computer, diagonalize this operator, you find the eigenvalues. And we are interested in the leading eigenvalue. And let's label the leading eigenvalue as k of lambda. It's labeled, it depends on lambda. And the goal is to search for the solution with eigenvalue 1. So you just search, you just have the plot this function and look for the intersection with k equals 1. And that particular point, growing exponent will be called, will be identified as the Lyapunov exponent. And this is the usual recipe to compute the Lyapunov exponent. And now we have fugacity. So what we do is just simply multiply this fugacity on the kernel, and we get a generalized equation. The fugacity times kernel, and the Lyapunov exponent will be a function of mu, and you still search the solution at equals 1. So basically, you get the full information of this Lyapunov exponent as a function of mu by solving this. And the branching time, as we define it, is 1 over lambda derivative at mu equals 0, and just simple calculation gives you a form independent of the mu. So that's branching time will be the slope of this eigenvalue at the Lyapunov exponent. There's minus sign just for convention. You want some positive number. Okay, that's the recipe. So with this recipe, we can try to compute. We can try to do some computation. And since in the various spreading model, we find an interesting relation between the Lyapunov exponent and the branching rate. Now we can check whether this kind of relation also holds in the in quantum mechanical system with different temperatures, and that's what we can do. It turns out that if you do the calculation in the low temperature, there's a significantly different relation, and that's what we show here. So we have a definition of branching time, so we can compute the branching time. And we can also compute the Lyapunov exponent in the low temperature. In the low temperature, in the SYK model, is same as a strong coupling because the dimensionless coupling constant is beta j. Jo is coupling over the temperature. So in this limit, we find that the Lyapunov exponent is given by the maximum value 2 pi t and a small correction. The correction is inverse proportion to branching time, or is proportion to the branching rate. So it's alpha. Alpha is a positive number as related to specific heat of the model. The alpha over jt, and the branching time for the SYK at low temperature is some order 1 times the Lyapunov time. So it's 1 over 3 pi times temperature. The important point here is that there's a minus sign. So the branching rate actually slowed down the scrambling. Unlike in the high temperature case, we have intuition that the branching rate is the driving force of the scrambling. Branching is the driving force of scrambling, but here branching actually slowed down the scrambling. But given the chaos bound, that's the only possible thing to do. So you can only have minus sign here. And this kind of different sign for the scrambling rate in the high temperature and low temperature seems to suggest there are two different mechanisms for the scrambling. So in the high temperature or in the weak coupling, this formula seems to suggest the the scrambling is due to the branching, but in the low temperature, in the strong coupling, we have a different picture. The system scrambles very well without the branching, and the branching actually slows down the scrambling. This formula actually, well, is a side comment that this formula actually explains some puzzle at Q equals 2 SYK model. Q equals 2 SYK is a free fermion model. It's just a random hopping term, and the single particle spectrum is just semicircle, and that's a model with no chaos. In particular, the upper exponent should be 0. But for the SYK, for the Q equals 2 model, you can also derive a so-called Schwarzian effective action, and the fact that here is a 2 pi t is actually due to that low energy sector. So how to explain the tension between an integral model and a large Lyapunov exponent given by the Schwarzian sector? The actual solution is that the actual resolution is that the branching time in this case is 0, and that means the branching rate is so big that it basically cancels all the scrambling caused by the Schwarzian sector in SYK model. So I want to emphasize this significant difference in the high temperature and the low temperature, and I want to say that this is actually similar to what we experience in the daily life. In the daily life, there are 2 ways to scramble. One way is, for example, you want to mix honey in the water, and one way is just to let the system dissipate. You just have honey in the water and let it mix by its own. So you have hot water, you wait. So that's one way to scramble. That's using the dissipation. The second way is just to use a spoon, or you fancy a word you can say you are doing geometric deformation. You just stir the water and the honey in the mix in a sense that they don't have to bind in the molecule level, but you just make the honey spreads in water in a geometrical way. I want to make a comparison to the 2 mechanisms here, two formulas here. This high temperature picture is very much like the dissipation, because the branching has some similar flavor as the dissipation. Your simple object becomes more complicated. The second scenario is similar to the geometrical deformation, and actually in the actual computation SYK, you do find that the leading part is given by so-called Schwarzian sector or the reparametrization mode, and the dissipation part is coming from the other fields in the system, and that causes a slowdown of the Lyapunov exponent. Okay. Maybe I'm running too slow. How many time do I have?
You probably want to think about wrapping up in the next 5 to 10 minutes, or maybe 5 minutes would be better.
Okay. So that's good. So here I want to emphasize that after some computation, we realize that branching plays a significantly different role in high temperature and low temperature, and this seems to suggest 2 different mechanisms of scrambling. Now, coming back to this formula, the Lyapunov exponent in the low temperature is almost maximal, and the correction is proportional to the scrambling rate. So there's a natural question. So can we actually achieve the maximum chaos by parametrically enlarge the branching time? So is it possible to find a model with a parametrically large branching time? That's actually the beginning of the project. We're trying to find a model with large branching time, but it turns out to be a no-go theorem for a large class model. We found that there's a upper bound of branching time. This is the main result in the main technical result of the paper I just mentioned. So we found that for a larger class model, which I will specify very quickly, we assume that the Lyapunov exponent times the branching time has upper bound is upper bounded by 2. So you cannot find a very long branching time in the unit of Lyapunov time. This upper bound is applicable to, which I will specify, let's just call it SYK-like models. And those models has to be, for this bound to be applicable, has to be fermionic in the sense that each probing field has to be fermionic, but the rank function can be come from some bosonic degree freedom. And the second assumption for this model to be qualified as SYK-like is the thin rank condition. So this condition means this rank has to enter the rail at one point, not a large regime. In general, this ladder diagrams, so each rank is a summation of all the 2-particle irreducible diagrams. So that could be some general function of 4 times, not just the insertion time. Like for example, T1, T2, it should generally depends on 4 times. And to make the model simple and qualified as SYK-like, we assume they are just function 2 times, or in other words, this rank has to be very thin. But other than that, we can introduce more flavors to the SYK model in high dimensions and all kinds of that, and they all satisfy this relation. The branching time is upper bounded by twice the Lyapunov time. So this upper bound can be, well, it can be viewed as a no-go theorem, or it can be viewed as a possible guide, is a guide to find a model with large branching time. You just try to violate these 2 conditions. You can think about, for example, bosonic model, and think about, for example, matrix model, which doesn't have the thin rank conditions. Okay, so that's the upper bound. I will skip the ideal proof and make a few comments about the weak coupling limit. So in the beginning, I introduced the barrel spreading model, which is supposed to mimic the operator growth at high temperature, or in other words, in the weak coupling. So that's a classical model. Now we can actually verify all the intuitions we have in actual calculation for the quantum model at weak coupling. So what we can do, so what we assume is the quasi-particle, we assume the system has quasi-particles. That means that we assume the retarded Green's function is given by the following form. It's just a simple, has a simple pole at the negative lower half plane at minus gamma over 2. That's what we usually assume for the quasi-particle. And then we can insert into the kinetic equation and compute all the things we want. I will skip the details. What we found is for the weak coupled model, you can actually use some simple intuition from quantum mechanics to prove the branching time has a tighter upper bound. It's smaller than 2 over the Lyapunov exponent plus the quasi-particle decay rate. And well, that's not surprising because it imposes more conditions. You have a tighter upper bound. And what's interesting is under some approximations, you can actually compute the approximate value of this TB. It will be half of the upper bound. So it will be approximately 1 over lambda L plus gamma. In other words, in other way, we can write it as the Lyapunov exponent is approximately the branching rate minus gamma. And the approximation we made is that the rank function has a small range. Well, I don't have time to explain, but it's basically requiring that the Whiteman function in the system in the time domain doesn't, it has a localized form. And in particular, the Brownian SYK model will satisfy this condition. It's actually a delta function in time, so it exactly So it makes the approximation exact. So in the Brownian SYK, after computation, we will find the Lyapunov exponent is exactly the branching rate minus the quasi-particle decay rate. And the final comment I want to make before I go to the summary is that this approximation we use, although I didn't have time to explain, is the same. It gives the same result as the commonly used approximations used in the literature for those people who has been studying this problem before. Okay, let me skip this. Let me come to the summary. Yeah, so let me just review. Just trying to remember what we have discussed today. So we start from the picture explanation of scrambling at infinite temperature using the operator growth picture, and map it to a viral spreading model. And they use the viral spreading model. We define new time scale. We get some intuition about a new time scale called a branching time. And found an interesting relation in that viral spreading model. And then we go to the actual quantum system to define, to give a quantum definition of branching time using the kinetic equation methods, or the retired kernel methods. It has several names. And then we use this definition and to compute some examples. We compare the low temperature formula versus the high temperature formula. We use SYK as simplest example, but you can use other examples. And we found that the formula indicates there are two different mechanisms for scrambling in low and high temperature. And we also mentioned about the upper bound of the branching time. And in the end, we talk about what happens when you impose the quasi-particle form of Lagrange function. That's all what I have. Thank you.
Thanks for the very nice talk. So I think we can maybe take a couple of quick questions now. If you want to talk more in depth, we can have a discussion period afterwards. But are there any short questions now?
Mm-hmm.
I have a quick question. Under what conditions is this bound on the branching time valid? I mean, is this a SYK-like bound, or is it for more general quantum systems?
It's actually like bound. SYK-like models. We require two conditions. Basically, there are also other technical conditions, but those are not so important. The two important condition is the probable field. The field operator you use to compute the out-of-time order correlation function has to be fermionic. So basically, we want the interacting fields to be fermionic, but there could be some bosonic degree freedom, but they won't go to the rails. The second is called a thin-rung condition. That the Feynman diagrams is basically some of ladders that the intersection is only happen at a point, not a large range. For example, if you have a matrix model, that second condition won't hold because the two-particle reducible diagrams will have planar diagrams which expand in a large range of time. So that the bound holds when these two conditions satisfied.
So Yingfei, yeah, just related to the statement regarding the matrix. So if you can see the matrix model at weak coupling, then you still have the other formula which you wrote before. That still applies.
You mean this formula?
Yeah, you have a quasi-particle formula 2 over.
Actually, I didn't check, but I don't know. I think so. I think you assume this in that calculation.
Mm-hmm.
And what the approximation, for example, used in literature is they approximate GR times GA by a delta function in frequency space. So that's the basic calculation. The basic calculation is done.
Mm-hmm.
So I assume this holds for that.
Mm-hmm. Yeah, but for strong coupling matrix theory, you don't have any expectation.
Yeah. And the diagrams won't be as simple as ladder diagrams. So generally, you need to sum the planar diagrams. Mm-hmm. Only at weak coupling, there's a additional simplification. You throw out all the diagrams, for example, connecting like horizontal thing.
Mm-hmm. Mm-hmm.
Okay, so thanks for the questions. So I'm gonna end the formal session now, and I'll stop recording.